Yeah, good. Well, looks like the previous lecture was very much on what we were talking about. Lenz's law and loops and stuff. Okay, so get all that. Well, we're going to have a review. And now this is your time to ask questions. And I'd like to, unless it's a better idea, do the format that I had the last time, which is you propose questions now that you maybe have in mind. I can hopefully order them in some way that they make a coherent picture, and we'll go over them. So do you have some questions? Yes. I have my book too. 2013. Page what?
It's on one of the practice terms.
Okay.
And it's about. It's question number 3. After my brains are moving left to right along the z-axis, will encounter row of wires, 1 millimeter diameter, being 3 millimeters apart.
Ah. Right. No, we just actually happened to go over that in my office hour, so I remember it pretty well now. We just did it. Yeah, that's a nice question. Okay, let me write it down. That would be the wires and an electromagnetic field passing by. Uh-huh. It's sort of like a demo we did, right? Remember the microwave with the grill? Maybe you remember, maybe you don't. Okay. It has to do with polarization. Yes. Any other interesting questions? Yes, go ahead. Speed of, I tell you, we didn't go over that in class. That's a velocity addition type question. We didn't go over that in class, and I think I excluded that from the material. I'd love to talk about it, but that's really not on the exams. You can breathe easier. It's a very interesting question. Actually, it's an interesting question because it asks the question, if the speed of light is as fast as things can go, suppose I'm going very fast and I shoot out something also very fast, would not the sum of these two possibly exceed the speed of light? In other words, for example, suppose I was on an escalator or one of these moving sidewalks, and I'm just standing there. I'm moving, let's say, at 0.9 of the speed of light, and then I throw a ball at 0.9 of the speed of light. So the ball is already moving at the speed of 0.9, and I add 0.9 to it. Would not the ball be going at 1.8 of the speed of light, the sum? That would, in old-fashioned classical physics, that would be the correct answer, and it would exceed the speed of light. And the question is, how does Einstein take care of that? And so we have a different formula of addition, like V1 plus V2 is V total. Well, it turns out that when you're near the speed of light, that doesn't work. And there is another formula, but that is not on the exam. It's one less thing to worry about for you. Any other questions up front? No? Okay. Yes?
It's number 3 on the 2012 metrics. It's basically a combination of F equals LID. And it's...
Could I see it, please?
Sure. It's more the concept.
Yeah.
If you could just discuss, like, when...
Oh, okay.
It's not the Faraday one, it's the...
Okay, this is a wire loop with a voltage and a resistance. And the question is direction of the force. Okay, that's a good point. Is there anything else in this?
Not the calculation, just that, and also if we could discuss
the directions.
Yes, again, if that's okay.
Sure. No, that's very fine. That's a good question. It's a good question. So the question, actually, the exam question was basically I have a loop through which current flows. I think there was maybe like a battery. So we threw in here, in addition to the magnetic field is coming in or out of the blackboard, Jordan? It was coming in or out?
Sorry, it's going into the big
B field.
Yes.
Yeah. Okay, and then so this is kind of a combination question, which is fair now. That is to say, it includes a circuit with a voltage and a loop which has resistance. So we're using a little bit from the first part of the course, the V equals IR. And the question is, what is the direction of force? Direction, maybe magnitude. That's a nice combination question. Yes, again. I beg your pardon? Why antennas are half wavelength? That's a good question. That's that again about E&M fields antennas. Okay, yes, there.
I have two questions. The first was in class you talked about the analogy between the magnetic dipole and a spinning top of gravity. And I was wondering if you could explain that analogy one more time. And then the other thing I had a question about was on the slide there was an example of a wire grid, there being a transmitter, a wire grid, and then a receiver. And then depending on the direction of the wire grid, what would be received.
That's very similar to this, actually.
Yeah, but then, so maybe this is a weird question, but the wire grid, obviously it's a physical object, and then if the wire grid is letting horizontal waves through,
Yes.
Is that considered a horizontal polarizer?
Yes. Okay, so if I understand your question, how is it different from this?
Between a physical object, because in the slide you have the physical object.
The physical object and what do we call the direction of polarization? Is that the question?
I just wanted to know the understanding that I was coming to of it being an example of a polarizer. If that was correct.
Yeah, it is an example of a polarizer. This is how polarizers work, basically. They have some kind of a conducting wires in the thick wires in quotes, which are just long organic molecules which act like conductors, and so they absorb the electric field. That's what I'll try to explain it. Not necessarily, because they may not be conducting. You do have to have conduction. So a diffraction grating could be non-conducting material, but if it were conducting, it would polarize.
If it were not conducting, how do you explain that, like, it'll change based on the orientation of the diffraction grating? How do you explain how it changes the vertical or horizontal direction of the
Yeah. Well, you could think of a grating as just being a bunch of opaque. That's it. Okay. So that's a very fair question, actually. A grating. Well, typically we don't worry about that. You're getting into very new ground, very creative. But suppose a grating we're conducting versus non-conducting. That would be interesting, yeah. Well, typically we don't worry about the conduction in a grating because you can make them out. All you have to do with the grating is have block the wave from getting through and letting it through. And this could be just like a piece of paper, could be insulator. And typically they are. I think the gratings we handed you were little plastic sheets with just lines scratched in them. So you don't have to make them conducting. If they're conducting, all kinds of interesting polarization effects might start happening too. You might polarize the light that comes through. That's a basic answer to your question. Just, yeah, so you combine the effects. Fair question. It's a new invention too. Polarizing interferometer. Why not? Good, sure. Yes, go ahead.
Can I ask you a question?
Of course.
Yes.
Oh, what's this? This is the peak amplitude of voltage generated by a rotating. Which one? Oh, B. The moment shown, the page turn counterclockwise. What is the direction of the current? Okay, this is okay. That's that might come in here. The idea of a coil turning in a magnetic field. Basic idea. I think chronologically we took that second, turning. Okay. Make sure I get to the point you want. Well, anything else? Is this of interest to most of you? Okay, so let's do it. Okay. Well, look at all of this good stuff here. Approaching North Poles, dBdt. Oh, my goodness. I could probably... This is your question? Oh, gosh. Well, not quite. Close, and pretty close, though. Save me some writing. Well, let's do the first one first, because that's the basic... I'm not going to go on to this anymore. We could talk about that some other time, but it's very interesting what would happen if the gratings were conductors, which they are not, usually not. But the very first question is having to do with the basic magnetic force. And the idea is that if you had a battery and it was attached to a wire frame, which has resistance in it, the battery has its own EMF. It's pushing out a certain voltage, pressure. The current, by Ohm's law, well, let's analyze the question. It's put in a magnetic field, going into the blackboard. It means that there's a north pole here, and the lines are coming out to the south pole, which is behind the blackboard. Now, because of the voltage here, some current will flow, and we have the fundamental law that there's a force. This is the woman's lib thing, L I across B, that's the way I remember it, is the force on the wire carrying current. Depends on its length and so on. And the point being that it has this cross product, and the cross product means that you turn, if you have I in one direction, or let's make a big I, and you have B in the other, you turn I into B, and the force then is in the third direction by the cross product rule, right? We know that? Okay. Okay, so that's what's going to be going on here. Because this battery is pushing current through the loop, there'll be current going down this way, and that way, and back into the battery. Okay, so each of those currents, being in a magnetic field, is going to feel some force. So let's do that. We have I downward, and we turn it into the magnetic field going into the blackboard. So can we get the direction of the force? I see some people pointing... What I saw was a force that way by you, which is right, I think. Would you all agree on that? Okay. All right. Now, how about this one? Current going this way, field going into the blackboard. I'm getting up. All right, you got up. So So that's force on that one. How about this one? Current going that way to your left, right? Okay. Now the current is the same in this and in this, so these two cancel out.
Couldn't you think about this as centripetal force too, because it's
Centripetal force?
If it was
maybe.
a straight wire, if it was like in the Hall effect.
Oh, it's a Hall effect. There would
If
be
it were to be Hall effect, then it would
a Hall. You could think of it in a more complicated way. For this particular problem, I think it's straightforward to just consider the force on each section of wire that's soaked in the field. Is there any problem with that direction? Okay, so I think that it's pretty clear that it's the same current, and the way I drew it, more or less, it's the same length, so that the force on this side is equal to the force on that. So the net force is upward on that. Okay, so that answers perhaps one part of the question. What is the direction of the force? And then the other part of the question might be, what is how big a force is it? Now, the way I drew it here. Now, in the actual problem, I might have done something like had the current. This is interesting. Suppose the current were going in the other direction. Suppose, for example, I don't want to waste too much time on this, but if the current were going in the other direction, okay, now, and soaked in the same field going in, now I think I might have done something like this, put this on a spring balance, so it tells me the force or the weight. Is that actually the question that I posed? That would be interesting. In other words, let's see, if the current were going this way, the current is going this way, the field is going inward. Well, we know that these two cancel, so let me just worry about this one here. The current going this way, I cross B. Now the force is going down. So now the force on this is going down. So if this were on a spring balance, it would actually pull on the spring balance, and it would be a force going downward. And that would tell me the force as registered on sort of like a weight. Like the old-fashioned, you weigh your potatoes, and I don't know if you do that in Safeway, you put them on the scale. Yes, sir.
So if let's say this spring had a weight and this was like a current around the weight, then would the force and that force on the spring be mg plus?
That's right. Yeah, if I hung it on here, it would have its own weight. This, let's say even with the battery, the whole apparatus. So, right. So, right. That the spring would register first the mg of the wire plus battery. Okay. Then, if I turn on the magnetic field, it's going to go even further. It's going to weigh more. It's going to weigh more. If you want to look at it, that shouldn't make jokes before exams. I know it's very bad. But yes, the spring will stretch more. As the turn on the magnetic field, it will pull down further. Right? Do you see the feeling for that? Good point. Yes, it'll have its own weight, but when you turn up the magnetic field will exert a force on that current and force the springs further. Good? And the magnitude of that will be, I suppose in the problem I gave you the length here. I should have to do that. If I told you the battery voltage, so I give you the length, the current I get from Ohm's law. The current is equal to V over R. So if I gave you the voltage of the battery and the resistance of this loop, you would get the current in there. So I would plug that in with the current here, the voltage of the battery over the resistance, And if I told you the magnitude of the magnetic field, this would be the extra force pulling that frame into the downward. And it would seem like it weighs more. Pardon me, sir? That would be that case, yeah. Or in this case, it would weigh less. In other words, if, as she suggested, if I put this on here and I measured the mg with, this would help. It would lift it up. It would actually seem to weigh less. I don't know if it would push it right out of, to negative. It conceivably could make it actually go past, but it would sort of weigh less because it would be pulling it up. Okay? Does that make sense? So that's simple. That's the straightforward use of the magnetic force. Now, the next thing we got into was this idea, which has to do now with a turning coil in a magnetic field. Now, that should immediately turn your mind to the chapter on... You sound like a lawyer. I'm in chapter 11. No, it's, anyhow, induction. It's an induction effect. I've got a magnetic field, and I've got a turning coil. So, are we finished with this? Is this okay? Pretty straightforward. By the way, that voltage could be by anything. I mean, somehow if there's a voltage around this loop, it would generate a current controlled by the resistance of that loop somehow, right? And so the same laws would follow, which would actually apply to this next case, which is in a voltage induced in a coil. So this was your question, so make sure I get it right, what I'm doing here. Namely, I have a coil. Does it have some turns? More than one, maybe? Doesn't say? Several hundred turns? Okay. So we have a lot of turns. And the magnetic field was which way? Remind me.
Magnetic field going
directly upward? Okay. And presumably it's turning this way. So that sometimes, sort of like this. So it's turning this way, I think. So sometimes there's a lot of field coming through it, and sometimes not so much field coming through it, right? Okay, and so the question is...
at the moment shown, what is the direction of the current?
What is the direction of the current? Okay, direction. This is a little bit tricky. So let's try to, the geometry being a little bit funny, let me try to make this the side of the loop facing us. And the thing is, yes, thank you. What is the, peak amplitude? That's the first part. That was the easy part.
Yeah, that was easy.
The easy part was because it's a simple formula. The peak amplitude was given by the peak amplitude of a voltage generated out here was given by the Women's National Basketball Association. That's the angular frequency, the number of turns, the magnitude of the magnetic field, and the area of the loop. So that's the peak amplitude. Because what's happening, you're getting a sinusoidal voltage coming out of this thing, EMF, and the peak amplitude is this V, if you will. That's the peak amplitude. We derive that.
Is that the same as the negative of Faraday's law?
That is a negative of Faraday's law. That it comes from Faraday's law. That's equal to minus the change in flux, magnetic, with time, but multiplied by n turns, because every turn picks up one of these omega BA, and then there's another turn, which is in series with that one, which also picks up an omega BA, and if there are n of them, each of them is adding up in series. So you have one turn, which is a loop, and has an area, and it gets a voltage generated in it, but the next one is in series with it, so each one of those adds up, and the whole n turns add up in series to give you n times what one loop would give you. That's the theory behind that. So the question you really wanted to answer was B vector A. B is in the page, A is pointing out of the page. Yeah, that's a little different from what I drew. B is in the page. The loop is actually coming around this way. In this particular problem, right? As it happens. It says here, area vector A is pointing out of the page, B in the page, and the coil's turning counter. No, it doesn't make too much. Well, let's just say it's part like this. Is that what you're saying?
So both the field and the wires are in place.
At the moment, and the wires are turning this way.
Some direction.
Yeah. Let's say the wires. Say again.
Either way, if the B field and the loop are on the same plane, initially it's 0 flux, so it's the turning back or forward would increase in flux.
Yeah, well, I just wanted to. Well, let's do it one way or another. It doesn't. Let's see. The important thing that's happening is that the amount of what we're using again is the Faraday law, and the Faraday law says that the field EMF is the rate of change of the magnetic flux with time, and the direction is given by this minus. Tells you that you have to use what's called Lenz's law to find the direction. That's the minus sign here. So let us, for the sake of argument, let's consider just one loop with the loop. Will this be okay with you if I consider the loop this way and turning this way?
So the loop is in
It's turning toward us. Should we just do that one? Would that be good enough? Okay, and the question is the current going to be flowing in this direction, or is it in that direction? Through this is the front of the loop. Okay, and the question is the current going to go this way or that way? Okay, because we're going to generate an EMF around this loop, and if this conducts, the current will flow in the direction of plus, it will flow, well, in one direction or the other. And the question is, which direction will it flow? Now, how we label this is another interesting point. But the point is that here the key thing, if the loop is turning this way, because someone is turning it this way, the current is generated, but the current that's generated is going to be such as to oppose that motion. So in other words, if you're turning toward us, the force that is generated must be in that direction, opposite to the way it's turning, right? So if the force is in that direction and the field is in this direction, the question is, well, so this is at an angle here, and the field is this way. This is at an angle. The current, the current, I think, has to be in this direction. Oh, let's see. That's tricky. This is coming out of the blackboard, and B is this way. So I has to be in this direction because the force wants to be this way. In other words, the loop is like this. The current is going this direction. I turn it toward B, and the force is it has a component upward. So I think the current has to go in this direction. Pardon?
Isn't the magnetic field inducing into the coil, meaning it would go the other way?
The idea is that the changing magnetic field induces an EMF, which drives the current. The direction of the current is such that when the current flows, it interacts with that original magnetic field to give you a force. That force opposes the motion that created the changing field in the first place. So if the field, in other words, if the coil was turning this way, the force that is generated must be opposing that turning. So you find out if the current is this way and the field is upward, there is a component of force upward. So that would say the current would be in this direction around that loop. Another way of looking at it, let's see if it should give the same answer, is that as the coil is turning, the amount of magnetic field through it is increasing. So that looks like it's giving a somewhat different answer. The amount of field is increasing. So, now that would, and the argument would be that the current direction, that's interesting. The current direction would be such as to create field going the other way. Now that's giving me the opposite answer. Very interesting. You know, I like this way better, actually, of thinking about it. In other words, if the loop is turning this way, the amount of field in that direction is increasing. I like the idea that the current would flow in this direction because that would create a magnetic field through the loop opposite to the field that is increasing. You know, I like this better. This geometry is a little bit confusing, just how the force is going. Let's look at it that way, then.
Can you explain the other way?
Why the other way?
The one you just...
The other way, yeah. In other words, one way of doing this, and it also explains inductance, is that if you have a changing field, the induced field is opposite to the change, so that you'd get a sort of delta B induced. Now, this is, again, very hard to show, but if the loop is like this and turning toward you, the field is coming through here. There is more field coming through the loop. So the current that would be induced would be such as to produce a field opposite to the field that it would be downward. You see, the field that is increasing is upward. This field in this problem is vertical. And I'm turning the loop, and I'm catching more of it as I turn toward it. I'm catching more field. Therefore, the induced field is such as to oppose that increasing. The field is increasing upward by my turning. The current that I induce produces a field that opposes that increase. So that would say the current actually should be going this way. I don't know if I had that. No, I think I had it wrong the first time. So I think it's actually this way. If that's the loop, the current will be going this way. In other words, it will oppose it. It's a little hard with this geometry to see what is the direction of the force. So there are so many different ways of looking at it, all of which should give the same answer. But in this case, I think it's easier to think of the induced field will be opposite to the change, which is the same reason that inductors work. They also create a magnetic field opposite to the field change. What you want is the field is changing upward through the loop. Therefore, the current direction has to produce a field opposite to it, a delta B, downward, and that through the middle of the loop. And that is produced by a current flowing this way, which would say that this is, in a sense, the polarity of this battery. This is acting as a generator. Current will come out of the plus terminals. That is the long-winded answer to that, I'm afraid. Let's go on. Yes, sir.
For this question, where did the F come from again? Is it opposing the motion?
The F that is generated, in other words, that current that gets generated is an induced current, but it's the current flowing in the wire.
So the force is...
And so the force, now that's the trick. Yeah, the force on that front part of the wire, if the current is going this way and the field is going that way, you'll have a current. Yeah, you see, it's all tricky because you see that loop is kind of at an angle, and the current is here, and yeah, that makes sense. Yeah, the current is there. It's turning into the B, and the force is going into the page, which is opposing the motion. I said it was turning this way, so it is opposing the motion. The force, the force on this induced current is opposing the motion that created it. Yes, this works. Yes, this is right. In other words, I've induced this current. This current is now in this magnetic field. The force is given by I cross B. It's into the page. But I was turning it out of the page. So it is opposing the motion that created it. So that's the correct direction. It works both ways, yeah. So there's two different ways of getting it, at least, yeah. Is that okay? It's still puzzling. You can do it with QV, your way. That's another way. Let me let me try to go on to other things in the time we only have a few more minutes, although I'm willing to stay after 4 o'clock if you have time, so it's okay. But then we have this question of the wires and other issues like that. It's similar to the antenna story. Story here is that we have an electromagnetic wave, and they're all characterized by the fact that you have an E field, and let's, just for the sake of fun, put the B field this way when the E is this way. I'm sorry. Now, the direction of propagation of this wave is always in the direction, if you want to have C, it's in the direction of E cross B. And in this case, you see the wave is, the electric wave is doing that, the magnetic wave is doing this. They both peak at the same place, and the ratio of them is a constant as it happens. So at every point, they are related because they're creating each other. And so there is a definite relation between the two. And the direction in this particular drawing, can somebody tell me which way? Is the wave going this way, that way, that way, that way? This particular wave. Negative X. If this is X, yeah, negative X. There's a vote for negative X. Anybody else have an opinion?
What are we meant?
The direction of the velocity. Of the velocity. Any other votes? We have one vote for negative X. You vote for negative X. Negative X is ahead by 2. Anybody else? Negative X is correct, yes. E cross B. E turned into B. And so the velocity of that wave is in that direction. And it is C in empty space. So the wave is traveling along in that direction. Now the question is raised, suppose I put in these conducting wires, like a picket fence here. It's not much good. Oh, that's all right. What happens? The idea is you have two fields. You have an electric field and a magnetic field. If you have linear wires, the best thing to think about is electric fields because they're going to drive charges in their direction. And if you have a wire, the currents will be driven up and down the wire. Or if you have a wire this way and the field is this way, the currents will be driven back and forth, but they won't go so far because the wire is smaller in that direction. So you don't get as much interaction when an electric field is going across a wire. It interacts strongly when it goes with the wire. Does that make sense? Jim? Okay. So the point is that in this particular case, I think the problem starts. Does the problem start with unpolarized? Unpolarized. So what that means is that not only is E in that direction, but there's an E in pretty much every which way direction. And the corresponding B. Let me just draw the E since we are thinking mostly about the effect of E. These are linear wires, straight wires. So E is pointing in every which direction. The ones that interact most strongly with this kind of a barrier is the electric fields that are in this direction, up and down. So they drive currents up and down, which means that they have losses because the electrons moving up and down generate heat by I squared R. So if I get an I in here and there's a resistance in those wires, those electric fields are used up in passing the wires. So that coming through here on this side, if the electric field started out this way on this side, by the time it passes these wires, the electric fields in that direction are weak. On the other hand, the electric fields that were in this direction, they just jiggled electrons sideways, not very much, and they pass through. So when you're over on this side, you'll have electric fields in that direction remaining from the unpolarized light, and the ones in this direction will be relatively attenuated. So what happens in a case like that is the electric fields that are pointing perpendicular to the wires get through. That's the polarization. So that is the polarization direction of that setup. The electric field direction will be perpendicular to the wires. Yes, dear?
So if you have a polarized incident light ray,
Yeah.
and the electric field is parallel with the wires, will anything pass through?
Very much weakened. The question is if the had a single polarized light, would anything pass through? It would be attenuated, depending on details, but it certainly would be reduced.
I guess that was what
Pardon?
confused me about this question, because it's asking what are the directions after you pass the wires, so there's still other directions. They're just bringing things.
Yes, but yeah. So in general, we would say that this thing it acts as a polarizer, and the polarization direction is perpendicular to the direction of the wires. In a Polaroid film, what you have is not metal wires, but you have some kind of long-chain organic molecule, which what?
So in those you would get electric field, or the EM waves passing when the electric field is parallel with that.
No. Again, perpendicular to the chains, because the chains act like good conductors. And again, if the electric field parallel to the chains would interact with the chains very well, would interact with them. So they act just like wires. A long chain molecule would act like a long wire. And so that field would be killed off, and the one perpendicular would get through. It's a little bit tricky, but that's the way to think about it, that the electric field, if it can drive the electrons, say, up and down a molecule rather than across it, that tends to be absorbed. And so it doesn't get through. And it relates then also to the antenna problem, because what you have is an antenna where in fact, you want to absorb the energy because you want to pick up some signal. So you want that. So what?
That would then an antenna is parallel to
The antenna you want parallel to the electric field. And it will pick up the thing so that in a radio, for example, if you have a radio signal, typically you have a long wire like this in a radio tower, the ones out in the bay. Sometimes you see these things like a radio station. It will be broadcasting a polarization like this. It's good to have your antenna pointing that way because its electric field is up and down, and it will interact strongly with your antenna at home. And that's good because you want to pick it up. On the other hand, if you want it to go through, that's not a good thing. If this were a lot of wires like that, they would have picked up the signal and attenuated it because it got absorbed in the antenna. Yes, sir?
In that case, why is it that you say transmittance in a polarizer is E cosine theta for...
Say it again louder, please.
Transmittance for an electric field through a polarizer is E cosine theta, and
Yeah.
absorbance is E sine theta?
Yeah. Well, that's the polarization direction. It's not the direction of the wires.
Yeah.
The polarization direction. Yeah. Well, you see, that's the funny little terminology problem that we have. Namely, that we say the polarization direction is the direction it gets through. See, if you have a sheet of polarizer, the polarization direction is the direction you get. It's the polarization direction. It lets through that wave, the direction that E gets through. The wires are this way. The wires, or the molecules, are this way, and that wave gets through.
Oh, okay, I see.
Yeah.
The direction of the wires such as here should be perpendicular to your polarization.
So-called polarization direction. That's the funny thing that we have to play in our brain. Yes.
So in that, like the one you drew, after it goes through the wires, does it maintain the direction of propagation?
Yes. If it goes through perpendicularly, there's no reason for it to change unless you put it through some other medium that could twist it. Now, the only other thought here was the length of antennas. Well, that depends on the length of the antenna that radiates well. What you're trying to do is you have an oscillating source, a voltage source, which creates a voltage which is pushing electrons up and down wires. The idea is you want the electrons to go up the wire, and as they go up, this might be the negative side at this particular moment, and the positive side here. In other words, electrons are being driven here, leaving behind positive. What you'll get is an electric field between plus and minus at that instant, and that electric field starts to move out at the velocity of light, and the charges go up the antenna, and then they come down the antenna and switch. So they're sort of sloshing back and forth. In the meantime, this radiation is coming out. Turns out that you want, if you want a certain radiation wavelength here, you want roughly the same, you want this to reverse at the same rate as this reverses. You want the electrons to travel up to give you, say, this negative this field like this, and then to travel back down in the same time. So they have to go up and down in the same time as this thing goes out for one period. So that makes the distance this travel up and down about the same distance